Hello world. I felt like you needed another quick and easy tutorial while I finished the other builds. Remember, I've got the Pet Robot version 2, the Skullface AI repair, and that kid's cosplay helmet repair. This video ties into the last one. I want the helmet to have two LEDs that glow on and off with the push of a button. Nothing too complicated. In fact, the part that I'm struggling the most with is the battery placement. I'm using one 18650 lithium-ion rechargeable battery, which is generally safe, much safer than something like a LiPo battery. But I just feel kind of weird about placing the board and the battery all on the back of his head. What if the internal somehow got wet, or the charging voltage boost module fails and fries? If I put it any other place, he has to have wires coming down his back to a belt, and that could get snagged on anything and rip the entire thing apart. If I put it on the back of the helmet, I want the battery to be in a solid case, so that even if it exploded or caught fire somehow, he would be protected. I'm sure it will be fine since the foam he used is pretty thick, but you know, I don't want to take any stupid chances here. Back to the LEDs. Glowing an LED can be done in several ways. I'm going to show you how to use the 16-bit resolution timer called Timer 1 again, which is found in the Atmega 328P chip. If you have a different chip, don't worry, the concepts are all similar. We're going to use pulse width modulation in order to get this LED to glow on and off. The timer is going to set up a frequency, and then we will be sending out electrical pulses on pin PB1 again, which is attached to the placeholder for PWM labeled OCR1A. If you have no idea what I'm talking about, check out my previous videos on PWM and servos. The pulse width, or how long the pin is on PB1 at each cycle of our frequency, will be determined by an increasing step counter trick that you need to know. First, let's take a look at our breadboard setup. Here you can see we have our chip with the top here. We hook up our voltage of around 5 volts here and our ground right under it. Next, we hook up our LEDs to pin PB1, which is where our electrical pulses are going to be coming out of. Then we can hook their ground up to the same ground as the chip. No problem. Now you're ready to code. Let's see what we need to write and see. I'm going to be using Programmer's Notepad. You can use whatever you want. Let's go over this code. This is the entire code for our glow LED on and off program, written in C. You can see that I've given it a name, helmet, and then LED new B.C. Whenever you start a new project, it's good practice and it's a good idea to create a file and make that file the similar name, the same name without the .c as your .c file. And always remember to save your actual program with a .c. If you don't do it with a .c, it's not going to work. And also you need to make sure that you put in your makefile. I just copy the makefile from my last code and paste it into the new one, and then change the target to the new program name. So I'll go over that in just a minute. Taking a look at the code, you can see it's about 36 lines with white spaces included. So it's about 30 lines of code, which is not too bad actually. That's pretty low, considering that, you know, here this takes up a few lines, you know, the while, main, and then the includes, you know, those take up a few lines. So this is actually a very, very minimal program. However, it does take a little getting used to getting all of this in your mind. So I'm gonna explain everything to you very quickly and very simply, but I'm gonna do it in a different way than what you think. I'm not gonna go down and just do code like that. Like I said in my previous videos, that's not the way that people generally code. That's the way that Hollywood makes it seem. You're just used to that because somebody made a program that just prints a bunch of shit on a screen in succession, and we see that and we think, oh, that's them coding, but you know, they're just acting. It's just movies. So the real way to do it is to have a plan. So you have a goal, you map out what you want accomplished. So I would say I want an LED to glow on and off. And then I'd write another map, like a logic map next to that. How am I going to get that accomplished with a computer program? How am I going to do that? First, you need to know some of the things that you're going to need. So I have these two include files. I have the basic AVR input output header file and the utility delay header file. These are pretty much common in any program that you're going to write in C for the Atmega series chips. You might as well just include them anyway, just to make sure everything works. Later on, you're going to start including other header files, and then you're going to learn how to make your own header files and libraries and whatnot. So for now, this is all we need for this program. And let's just skip down to what I need. So what I need is a timer. We're going to use the same timer that we use for the servo, timer 1. And we're going to set that up to create our frequency. So every couple thousand microseconds, it's going to count through the internal clock. It's going to reach that peak of that couple thousand microseconds, and it is going to send out a pulse. And then the pulse width, the length, that the duration that the pulse is on is going to vary. And that's all pulse width modulation is. So you set a frequency of how often it does it, and then you set a pin to output electrical pulses for a certain length. And the cool thing is, I'm going to show you a trick that we do in order to make this work. So we need to set up a timer here, and this is how we set up this timer. This is we're going to access timer 1, which is the 16-bit resolution timer. However, there is no switch to flip on to turn on timer 0, which is the 8-bit timer, timer 1, which is a 16-bit timer, or timer 2, which is another 8-bit timer. There's no switch to flip on these timers. What you're really doing is just going in, you look at the data sheet and you go in and then you find out what bits to flip on. So you flip these two switches and then it accesses timer 1's fast mode. So you can see this is part 1 of 2, this is part 2 of 2. So you need both of these bits to flip on, and this is called an OR operator. We don't really need to go into this yet. This can get really confusing as a beginner, so I don't like to cover the operator. This is called an operator. This is how you turn things on and off. It's very simple, but it's actually very complicated for beginners to wrap their head around, so we'll cover that later. So for now, just think of this as, you know, in Arduino language, I say digital write. That code, they write digital.write, and then they have the parentheses, and then you say, you know, whatever pin you're turning on. Digital pin 1, right? Oh man, it's been a while. So here in this TCCR1A, this is a control register. That's what the CR stands for, control register. So in this, on the data sheet, you can see these two bits are flipped, and that turns on timer 1 fast mode. Slow mode might not produce a good effect. It might not look as smooth. It'll be a little bit slower. Also, I mean, you could use whatever you want, but we're just going to use timer 1. Next, TCCR1B register, we flip the CS11 bit. So if you go onto the data sheet for the Atmega 328P and you look at timer 1 in that data sheet, you'll see if you flip this bit on in this register that it's going to pre-scale the internal clock. So this chip is running at 8 megahertz, and it's going through, it's counting all the way through 256 steps, which is 0 to 255 because it includes 0, and it's going to loop back around to 0 and do it over and over and over again. And it has 8 million clock cycles per second. 8 million hertz. So 1 hertz is like, you know, 1 clock cycle per second. So 8 megahertz, that's 8 million times per second. That's insane, right? And your computers that you play games with can do even more. So you can just imagine how fast these things go. So we're going to divide that by 256 with this bit. There's other bits that you can flip, and you can look at the data sheet. I challenge you to do it, because the more you look at the data sheet, the better you're going to get this, and you're going to be much more advanced than anybody in Arduino. So go ahead and take a look at those. We're going to divide by 256, which, if you do the math, it comes out to 13,250 microseconds. And 1,000 microseconds is the same as 1 millisecond. So I'm not very good at math, but look, 13.25 milliseconds is the frequency, basically. So every 13.25 milliseconds, it's going to complete a loop. It's going to go whoop, 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 whoop. And then in this control register A, we go back in here. I don't know, they just put them in here just because that's where they decided to put them in. They have good reasons, so don't worry about why they're in register 1A and 1B. Don't worry about that. So in this control register, we flip this bit, the COM1A1 bit, and that's going to set the pulses that are coming out at our frequency on PB1, pin PB1. We used that in our last servo video. And that is connected to OCR1A. You could think of OCR1A, OCR1B, OCR0, or yeah, you could think of all those. There's 6 PWM like placeholders. This is like a Tupperware container. So we're gonna put our number in that Tupperware container, and then that Tupperware container is what's used to send out the actual pulse. And our duration of the pulse is what we're going to set this to equal to. And so we're gonna get to that in a bit. So remember, we got the curly braces here. And the reason why I have void in here is because there's no parameters for it to take into account when it does all this. It doesn't need to depend on any other variables or anything like that to do this. When we did the ADC with the joystick, it needed a parameter to look for what channel to go on, and that's very complicated, so don't worry about it. So this is how we set up our timer for our frequency and for our output. Next, you'll notice that we have the timer with the same name. Next, you'll notice we have the timer and we're calling it in the main section of our code. So remember, we have this written here and we have our curly brace here and here. So this is the open door, this is the closed door. Always open and close your doors as you go in the houses and out of the houses. Timer setup, parentheses, semicolon. Remember to end all of your stuff with a semicolon, and that brings this timer into play. It says, hey, come on up, it's time to play. So he's ready. Data direction register B, which is the street with all the PB pins, is going to be set to output. So this turns PB1 specifically to output. So it's like opening the gate. That's why I wrote it here, opening the gate. So you're letting it open so that the electrical pulses can come out. This we assign the pulses to go out on that one. This one actually opens the gate for it to happen. All right, moving on. Don't worry about this. We're going to come back to this and these defines in just a second. So in order to get the pulses to vary in length, we need a for loop. What's happening is your eye is too slow to see this effect, and your eye perceives it as a glow. Most people think when they see a glowing light that the voltage is varying, like it's increasing in voltage slowly, and that's what makes it glow on and off. In the analog world of things, that's true. In the digital world of things, which is what we're working with, that is not true. The digital world simulates the analog world. And this is really important for you to understand when you get into robotics and electronics in the beginning. Everything you do is simulating the analog world and interpreting the analog world. You're translating it into digital values and digital things. So how can we simulate what an analog wave that would go up and down like that, where it glows on and then glows off? How can we simulate that in the digital world? The way to do it is really interesting. You have to vary the length of time that the pin is on. So it's sending out the 5 volts of electricity exactly the same every time. It's 5 volts, 5 volts, 5 volts, 5 volts. On, off. On, off. That's what a square wave is. On, off. On, off. So that's what we're doing. But what we're doing is we're changing the duration that it's on. And your eye can't perceive it very well. Because your eye, maybe your eye sees it. It goes into your eye, but your brain can't perceive it, which is fascinating. So we're going to have very short durations that it's on, and then it's going to increase in time as we go on. So it simulates our digital on, off, on, off, on, off. The time is going to vary, and it's going to simulate that wave, that analog wave of glowing on and glowing off. So this is how we do it. In our loop, so here's the curly braces, right here and right here. So in our loop, we're gonna have a for loop. This is called a for loop. These are crucial for you to learn, so pay attention. In our for loop, we have these parameters. These are the rules for this for loop. So we're gonna make a number, and I labeled it N. You can label it whatever you want. Some people label it X, Y, Z, who cares? So I have an unsigned 8-bit integer, 8-bit variable that is labeled N. You could label it, you know, I, X, it doesn't matter. I used N for, you know, number. So an unsigned integer in the program actually takes up less memory because it's not plus or minus, it's not positive or negative. If you do a normal signed integer, it can be positive or negative. It takes up more memory. For this program, it doesn't matter because it's so small, but that's just something that you need to know. And anyway, moving on. So we have our timer called, we have our pin set to output. In the for loop, we're gonna use this 8-bit placeholder that we labeled N, and we're gonna set it to equal 0 the first time it goes through the loop. Your code goes from the top down. It initializes from the top down, and then it loops back around here, and it goes back here, and it goes back here again and again and again forever. So we have N set to 0, and then we have to have a semicolon, and then another statement for our parameter is as long as N is less than 255, meaning as long as the steps in the 8-bit counter is less than its maximum value, we're going to do this. And every time we do it, we're going to increase it. We're going to increment it by 1. That's what the plus plus means. The plus plus means take whatever N is this time and increment it by 1. Add to it. So these are the parameters for the for loop, and what we actually want done when these conditions are true, when these conditions are met, we're going to have a delay, a short delay. So this is why I included this header file, util_delay.h. This is the function, delay underscore delay underscore ms, and then the parameter is going to be a value. So remember, in my previous videos, you could write a number, you can write whatever you want. So I predefined these values here just to show you how to do it. So you go up here and you say define. I said LED underscore delay A. That's just what I labeled it. It's just what I decided to do. And I made the value 10. So it glows on. So it'll turn on. It'll go through this delay of, you know, like 10, and then it'll set OCR1A, the length of the pulse, to N. So OCR1A is set to N. So in the beginning, it's going to be, you know, 0, and then it's going to have the very quick delay, and then it's going to do, you know, turn it on for 0. So it's going to be off basically. Then it's going to go back through the loop to the beginning, and then it's gonna check for these parameters if they're still true, and it's going to increment it, and it's gonna have the delay, and then the new value is gonna be 1. So remember, all this is doing is, in our chip, it does 8-bit calculations, so it can count from 0 to 255. That's 8 bits is counting from 0 to 255, which is 256 steps total because you include 0. And it just increases it by 1. So every time it's going, the duration is becoming increased by 1. So it's on for a longer and longer and longer time each loop around. What happens when it gets to 255? I told it to glow off. If I didn't, it would just stay on. It would just stay on. It would glow from 0 to 255, and it would just stay on, basically. So what I did is I had it glow off. So I did the same thing, but I changed the parameters. So when the number reaches the maximum of 255, and as long as it's greater than 0, if it's not hitting 0, which is true, we're gonna decrease by 1 step, by 1 count. So we're gonna -1 every time we go through. And then I noticed that my eye perceives, if I use the same value for glowing on and glowing off, it doesn't look as good. It doesn't look as cool. And that's because your eye perceives percentages of changes, not necessarily the actual increase and decrease. It's really weird the way your eye perceives light. It's not linear. OCR1A, we set it to N. So it's gonna decrease every time. So that makes it glow off as it counts through 255, from 0 to 255. So it's basically the same thing as this for loop in reverse. So make sure you got your curly braces, and you can just click next to them, and usually it highlights to make sure you got them all in here. Remember, all this pink stuff, these are my comments, so they're not included in the actual code. The compiler's just gonna throw that in the trash. But for you and for me, this helps to keep track of what I did and why I did it. And that's pretty much it in a nutshell. So you can play with this. Remember, save the file as a .c file in a folder that's similarly titled to your actual C file. Make sure to put a make file and change the target that's being flashed as your new program name, otherwise it's not going to work. And the make file is what helps you to actually flash the code to the chip, so it has to be in that same folder that you saved this .c file. And then in tools, I just click make all, and let's see it down here. Oh. Make this bigger. So all we got to do is, I like to make clean just for good practice. I make clean, so it cleans everything out of there if these files were in there. And then I say make all. There's no errors, and you can see everything was, you got the ELF file, you got the object file or the .o file, you got the hex file, you got all this stuff. It's ready to go. Remember, the hex file is the one that we're actually going to flash to our chip. And then if you have it all hooked up correctly, you just click program and you're done, and it should work. So let's take a look.